There everybody, welcome back. Well, graph cities. Let's go to the next problem. Lead code 310. Minimum height trees. It's a medium level problem and it is given with a hint. Seems like it is a bit tough. It is a bit on a tougher side. So let's see what's up. What is it up to? And the problem statement goes like this. A tree is a undirected graph in which any two vertices are connected. Any two vertices are connected by exactly one path. In other words, any connected graph without simple circles is a tree. Okay, given a tree of n nodes labeled from 0 to n minus 1 and an array of n minus 1 edges, where edge of I equals to ai bi indicates that there is an undirected edge between the two nodes A and B in the tree. You can choose any node of the tree as the root. When you select a node X as the root, the result tree has height h. Among all possible rooted trees, those with minimum height are called minimum height trees. Return a list of all minimum height trees, root labels. You can return the answer in any order. The height of a rooted tree is the number of edges on the longest downward path between the root and a leaf. So here we got n equals to 4. Let's see the constants too. N will be between 1 and 2 into 10 to the power of 4. Edges will be n minus 1. And the node values will be between 0 and n minus 1. And no two values will be same. All the pairs are distinct. The given input is guaranteed to be a tree and there will be no repeated edges. So we got edges and let's first print. No. So here n equals to 4 and edges are 1, 0, 1, 2 and 1, 3. 1, 2, 1, 3. Okay. So actually all of them are same, but we have different roots for each. For example, we have 0 as root here and you can arrange this as the same. We'll have a root as 1 and 2 and 3 and the root is the node with label 1 which is the only MHT. As shown, the height of the tree is 1 when the root is the node with label 1. So in this case, if 0, 2 and 3 are the root, 1, 2, the height will be 2, but in this case the height is 1. And for this case, 3, 0, 3, 1, 3, 2, 3, 4 and 5, 4. 1, 2, 1, 2 Output 3 and 4. Okay. 3, 4, 3, 0, 3, 1, 3, 2, 4, 5. Well, actually both are same, but we select a different route here. If we select 5 as a root, then we'll have 5, 4, 3 and 0. Well, this seems tough. Let's take the hint. How many entities can a graph have at most? How many you say? 1, 0, 1, 2, and 1, 3. Very vague hint, guys. Of topological sort. Well, I couldn't think of a solution. Let's not waste time. Let's at least try to think what can we do with the given input. We got input unequal to 4 and edges. To say the minimum like the maximum number of edges is n minus 1, right, but let's see how we define a level. Like, how can we think of a level? For example, we have 1, 0, 1, 2 and 1, 3. So we can have a level of 1 with 1, and for if we start with 2, we have to go to 1, and from 1 we'll have the remaining. Well, let's not waste much time. Let's take the help from GPT 310. With, minimum height trees. But what? Let's see what we'll get. Let's build our non-neural step by step and gradually lead you to the correct approach upon restate the problem neural nodes. You have to find all possible root nodes such that if you root the tree, At this node, the height of the resulting tree is minimized, basically which node makes the tree as balanced or shallow as possible when used as roots. Then I approach the one you thought of exactly what you said. For each node, pretend it's a root. Compute height by BFS or DFS. Take the nodes with minimum height because BFS for each node falls order of a tree with a node. So you need something better. Tree center. In the tree, the minimum height tree roots are the center nodes. That's for sure. Obviously, we know that of the longest path called the diameter. Think of it like leaves are farthest from the center. If you keep removing leaves layer by layer, what remains of the center nodes? Leaves are far, okay. If you keep removing leaves layer by layer, what remains the center nodes? So the pre-processing intuition you mentioned, it gradually trimming the tree until only center remains. While leaf trimming works, each iteration remove all current leaves. Okay, when you remove leaves, their neighbors become new leaves. But keep repeating until then are equal to two words remaining. Okay, wait a minute. Words. Each iteration remove all current leaves. Note with the given. When you remove leaves, their neighbors become new leaves. Keep repeating until less than or equal to two nodes remain. The center of the tree lies in the middle of its longest path. Repeatedly removing leaves from outside peels the tree inward until only the centers remain. See the empty edge. The algorithm process each node and edge once, so order of n time and order of n space. Here's the hint flow. Well, let's see. Build a adjacency list for the undirected graph. Adjacency list. I have to remember this term. Okay. Identify all initial leaves. Degree. Whose degree is 1? Okay. Well, the number of remaining nodes is greater than 2. Number of remaining nodes. Remove all current leaves. For each removed leaf, reduce its neighbor's degree. If a neighbor becomes a new leaf, add it to the next layer's list. N equals to 6 and this at these initial leaves are 1, 2 and 5. Okay, 0, 1, 0, 2, 0, 3, 3, 4 and 4, 5. So the leaves are 0, 2, sorry, 1, 2, 3 and 5. No. 1, 2 and 5 because 3 has 4 in between and we have 4 and 5 connection. So the initial leaves are 1, 2, 5. If you remove them, then we'll have 0, 3 and 4 and we'll remove 4 as well because it is a remove them new leaves. 0, 3 and 3, 4. If 1, 2, 5 are removed, you'll have 0, 3 and 4. How did 3 and 4 become leaves, huh? Something is not correct. So for n equal to 6 and edges are 3, 0, 3, 1. 0, 1, 0, 2, 0, 3. 0, 1, 2, 3, 3, 4, 4, 5. 0. Let's see. This is not great. So to start, 0, 1, 2 and 3. 0, 1, 0, 2, 0, 3, 4 and 4, 5. 4, 5. So if we remove all the leaf nodes, this is a leaf and this is a leaf. So if we remove them, then we will have we remove the 5. In this case, we remove these two. Now we have 4 as a root. We remove 4 as well. Oh, Oh, 'Well, it seems great. So, well, whatever it is. Oh, 01, 02, 03, 1, 2, 3. If I select 3, and degree. So, it is right. So, for 3, 1, 2, 1, 2. For 4, 1, 2, 3, 1. Same as 0. Let's not burn our motivation. So, let's take a small break and come back again to the problem. I'm back, the rest is over. So, let's go start our thing. Well, let's go through the instruction once again and see. So, initially, we have to do some pre-processing adjacency list. Let's see. Uh, I didn't remember adjacency list. I believe I have to record every adjacent node of a node and identify all initial leaves. A leaf is something that has a degree 1, that is it only have one, what do we call it, edge attached to it, while the number of remaining nodes is greater than 2. The number of remaining nodes is greater than 2. Remove all current leaves. For each removed leaf, reduce its neighbor's degree, and if a neighbor becomes a new leaf, add it to the next layers list. Next layers list, huh? Next layers list. Now let's see. Let's first try to build the adjacency list. So from previous, let's keep parent equals to mm, let's keep it adjacency, or let's keep adj. We go through every edge for edges. A comma b equals to edge. Now adjacent of a equals, let's keep it as a default it. And same goes in the reverse order. Now let's print this out. Now adjacent nodes to 1 are 0, 2 and 3, and for 0 it is 1, 2 it's 1 and 3 it's 1. And how do we calculate the degree? Maybe the length will tell us what the degree is. Let's see from here. We have 1, 2, 0, 1, 2, 4 for 3 as its adjacent values, and for 0 it is 3, and for 1 it is 3, and for 2 it is 3, for 4 it is 3 and 5, and for 5 it is 4. Well, let's see. Now we'll do we go while path. Let's see it again. The ladder begins and when the number of remaining nodes is greater than 2. I couldn't understand what the number of remaining nodes will be. Let's see. Hmm. Let's think away. If we remove this 0 and this 1 and this 2, then we have to remove 2 from here. 0, 1 and 2 from here. We will have only one value, and 4 will have 3. Three and 4. Let's see. Of is greater than 2. Of we pop it out. Now oh, oh, Seems like this is working, but I'm not sure if it helps. Let's see again. This will work for these small cases, but what if it is even more deeper, like 5, 6, and 5, 7. One, two, three, four, five, wait, well, that's what I thought. What if we keep it as a set? Nah, let's keep another list. Let's keep it as a set. Let's see now. Didn't help. Let's take help from GPT. Wait out. Yeah. Temp creates a dictionary, not a set. Oh, wait a minute. We're writing our temp before adding anything. Temp equals to set. For ending, for inside a loop over edges and set. Instead, first collect all links to remove, then delete them in a separate step. Removing edges incorrectly. So they remove by index, not by value. Then so posture means index. Okay. Removing edges incorrectly. Correct. Let's see. Okay. If length of one and then two. Okay. We're creating adjacency list here. uh, for node node of node equals to, I for in edge of node if I not in temp. Wait a minute. Well, I got what's going wrong here. Now this shall work fine. So let's submit it and see if it is working fine. Oh, well, it is taking so much time, but at least our solution is right. We almost did everything except for one, which took so much time. So it got time limit exceeded. Well, let's try to optimize it. Now, what can we do such that it will be optimized in terms of time complexity? Let's see. Let's copy this thing. Sorry, let's copy this thing. See, from here we created adjacency list and leaves. We created leaves node for node in edges length of is equal to 1. Well, okay. Oh, let's use list comprehension. For I in if length of is 1. is length of I have to clear the temp. Let's see the ChatGPT solution 2 when n is greater than 2 and minus equal to length of leaves. Well, this is one good solution. We keep a new list for leaf and leaves. Neighbor equals to adjacent leaf. Okay. Mhm. Out. So very close to the optimal system. Here we remove nodes before touching the edges when the name of this. So for leaf in leaves, well, let's copy this out. Oh, that's a significant boost. Let's go through what we did wrong and what's new here. Instead of keeping a list, we are now storing in the dictionary, sorry, set. And if the length, the leaves is same, while n is greater than 2, while we are removing the number of leaves, and we are adding new leaves. So for leaf in leaves, we are going through each leaf, and we are first we are taking a neighbor from the leaf. I mean the leaves neighbor. We are taking the leaves neighbor, and we are removing the neighbor. Like from the neighbor, we are removing the leaf. So what do we call it? Set Python set remove. Yes, great. This method also removes the element from the set. Unlike remove, if the element is not found in the set, it does not raise an error. The set remains unchanged. So we are taking the leaves neighbor. The leaves neighbor will be only one thing. So we are removing that neighbor. I mean leaf. Since we removed the leaf, we are removing leaf from its neighbor 2. I mean both leaf and the neighbor are, what do we call it, mutual neighbors. So since we are removing the leaf, we have to remove the neighborhood from its neighboring nodes. So we are removing it. If the length of the neighbor, if it is a leaf again, then we are adding it into the new leaves set. Why are we deleting the adjacent leaf? Edge of leaf, huh? Okay. Leaves. Well, let's submit it. Everything is fine, but we have to understand why n is why for n greater than 2 this is the case. Let's think it through. Let's see the image again, and maybe it will help from understanding. If we remove all the leaf nodes, we'll have 3, 4 and 5, and from here we'll have 4 and 3. So for any undirected acyclic graph, the minimum height tree can only be 2 or 1, just like a median. You speak, intuitively speaking, from center will have shortest distance center. There's exactly one unique path between any two nodes. The diameter of the tree. Path between two nodes define the span of the tree. Now think of the center of the diameter. In the middle of the triangle, those you are a single median where the diameter length is odd. Yeah, that's it, guys. So let's talk the intuition here. Before talking the intuition, let's see why this is taken 2. For everything, I mean, for every question, the answer will be either 1. I mean, the length will be either 1 or 2. And if we find a node which is, if there is a center node that have, well, there is two possibilities. one a center node with the distance from the node to the leaves for every leaf is same, or at least the maximum, right, every leaf is same. And the second, where we'll find one side of the leaf has smaller distance than the other side. In the second case, we will have two values, and for first kind we'll have one value, and that node will be in the center. So what we are doing is we create the adjacency list. Now from the adjacency list we are checking the leaf nodes. Leaf nodes are the nodes that have only one edge. Adjacency list will have uh, a set with number of nodes between n to maybe 1 to n. We'll have at least one node, or I mean at least one edge, or n edges connected to the n minus 1, actually n minus 1 edges connected to that node. So here we are checking all the adjacent values, which are the, what do we call it, the edges. So while the number of nodes is greater than or equal to 2, we are continuing. We remove all the leaves. So n minus the length of leaves, and the new leaves, as we remove the old ones, we are taking the neighbor of the leaf, and from that neighbor we are removing the leaf, because the neighborhood was cancelled because leaf was removed. Now if the neighborhood becomes uh, of length 1, because we removed one value from the neighbor, if the neighborhood becomes alone, then it is considered a leaf, and we are adding it to the new leaves. And finally we are deleting the adjacent leaves, because we are not actually removing the key entirely. We are popping the set value, and here the item will become 0. I mean, it the key value will be empty set. So we are removing those empty sets and assigning new leaves to the leaves, and the entire process goes until we'll have n is greater than or equal to 2. And let's see if it can be optimized even more, and let's see other solutions as well. Okay, adjacency list. Well, they did the same. So I hope you guys understood the inclusion. If you like the video, upload it and share it with your friends. And for the time complexity, let's see. We'll take order of n time complexity. We're going through the leaves. Well, we remove a complete layer of leaves. So n is the number of nodes actually. So you're attending every node. So the time complexity of uh, the entire thing is order of n. I hope you guys understood the intuition. If you like the video, upload it and share it with your friends. Well, my articulation for this video might be a bit cranky, but I sure will make a better video on this. So keep on touch and comment if you feel like intuitive with me. So thank you for choosing the channel for now. Subscribe to the channel and support it and share it with your friends and community. We'll meet you again with another video. Until then, keep pushing hard and keep learning, guys. Goodbye.